Can everybody see the screen?
Yes, ma'am.
Okay. So far we have done this first isomorphism theorem, and yesterday we have seen that when a group can be written as product of two of its subgroup, what are the conditions we impose on the subgroup so that the group can be written as product of its subgroup. And today we will do with the two more isomorphism theorem, the second isomorphism and the third isomorphism theorem. So today I will try to finish with the six isomorphism theorems, and then from next week I will start group action and Sylow's theorem, which are the main two topics of this group theory. Okay, so let's start. Yes, somebody is saying something.
Ma'am, yesterday exercise second I have not get the mapping properly.
So maybe we will discuss again on the next tutorial. Okay, let's do a
Okay.
little bit of theory today.
Thank you.
Second isomorphism. So what does the second isomorphism theorem say? So before defining what is stating second isomorphism theorem, let me define what is a normalizer. So for a non-empty subset A of G, define the normalizer as the normalizer of A in G. This is the notation to denote the normalizer. This is the collection of all the elements of the group G such that GAG inverse is equal to A. That means, in some sense, it is saying that what are all the elements of this group G such that we are, so A need not be a normal subgroup. That means for all G, this equation need not be true, but I'm trying to find out for which G this equation is true. Okay, and calling that set to be the normalizer of this A. So I'm trying to figure out which elements of this group are satisfying this relationship. So if it is satisfies for all the elements of the group, then we call A to be a normal subgroup. But in general, if it is not, then that means as if your this normalizer is going to be the whole group, that means your group is a normal subgroup. Okay, so if this set is very small, that means this group is becoming behaving very bad in the sense of normal subgroups. Okay, so this is measuring that how far it is from being a normal subgroup in some sense. Okay, so this definition is clear. Please mute yourself, everybody. So is the definition clear to everybody?
Yes, ma'am.
Okay. So now using this definition, we will state the second isomorphism theorem. So I will start with let G be a group. And let A and B subgroups of G. And assume that A is a subset of the normalizer of B in G. Then the first thing it says that A intersection B. So A and B are two subgroups. So A intersection B will again be a subgroup. But with the assumptions that A is a subset of the normalizer of B, this becomes very special in the sense that this intersection becomes a normal subgroup of A. maybe I will write in words. Then this is a normal subgroup of A. And not only that, it says that AB quotient B is isomorphic with A quotient A intersection B. So it says that these two groups are in fact isomorphic. Okay, so A quotient. So since A intersection B is a normal subgroup of A, so I can talk about this quotient group. This quotient group only makes sense if I go mod by a normal subgroup. So first I'm showing that this is a normal subgroup. So that's why this quotient subgroup makes sense, and it is saying that this quotient subgroup is in fact isomorphic with this quotient. Okay, so mainly we will be using the first isomorphism theorem to prove the isomorphism, but before that I need to prove that A intersection B is a normal subgroup of A. So let us first try to prove that A intersection B is a normal subgroup of A. So wants to show that A intersection B is a normal subgroup of A. So in order to show that it is a normal subgroup of A, what you have to show? You have to show that, so let us start with any element X belongs to A intersection B. Then I would like to show that G inverse belongs to A intersection B for all G belongs to A, right? If I want to show that this is a normal subgroup, isn't it?
Yes, ma'am.
Ma'am, B is a normal subgroup. How we assume?
B is a normal subgroup. We are not assuming B is a normal subgroup.
Then ma'am, quotient will not define. Quotient defined only when. Okay.
We will see. We will see. We will see. Okay. First, let's go step by step. Okay. So first, A intersection B is a normal subgroup. That's what I want to prove. So I need to show A G inverse belongs to A intersection B. So now what is G inverse? G inverse. G is from A. X is from A intersection B. So this belongs to A, right? Correct? And also G inverse. So this X is in B. This X is in B, right? So now G inverse. This G is in A. But what is the hypothesis? Hypothesis that A is a subset of B. What does that mean? That means that G inverse is equal to B, right? So therefore this element belongs to B as A is contained in the normalizer of B. Is this clear?
Ma'am, can you explain this once again?
Yeah. So what does it mean that A is subset of normalizer of B means what?
GB G inverse equal to B.
GB G inverse is equal to B for all G belongs to A, isn't it?
Yes, ma'am.
So that's what G inverse will belongs to B for all G belongs to A because X is in B.
Okay, ma'am. Understood.
Okay. So that means this G inverse is in A as well as in B. Therefore, Therefore, Gx G inverse belongs to A intersection B for all G belongs to A. Hence, A intersection B is a normal subgroup of A. So the first thing we have proved. Next, I would like to prove this isomorphism. So I will prove this isomorphism by using the first isomorphism theorem. But before that, you need to check the following. In general, this for any two subgroups, AB need not be a subgroup, right? But in this case, AB is a subgroup. Why is that? I have this assumption that A is a subset of normalizer of B. So you use this to prove that AB is a subgroup. Do you get the point? With this assumption that A is contained in the normalizer of B, try to prove that AB is a subgroup. This I'm giving you as an exercise. If you are not able to do, next class you tell me, I will do. But first you try. Okay. So this is one exercise you should check. Okay. Now I said that with this exercise you have proved that AB is a subgroup. Now I said I will use first isomorphism theorem. So for first isomorphism theorem, I need to define a map. So let us denote this map by phi A intersect A quotient A intersection B. Okay. So I am defining a map phi from AB to A quotient A intersection B. How do I define this map? Take an element from AB. It will be of the form AB. So phi of AB, where should I send it to? I need to send it to a left coset of A intersection B. So where should I send it? Somebody? No idea.
Is it A left coset of AB by A?
That means you are sending it to the corresponding left coset of A in this quotient ring, right?
Yes.
That is what you are suggesting?
Yes, ma'am.
Okay. This is the only way where we can send this map. I have this AB element and then I need to send it to a left coset. So I will take the corresponding left coset of A in this quotient ring. Okay. But then I have to check that this phi map is well defined. That means wants to show that phi is well defined. So for that, what I need to show? So if I take two elements, say A, B and A1, B1, then I would like to show that they are getting mapped to the same left coset. That means phi of AB is same as phi of A1, B1, right? So they are in the same left coset means what I have to show? If I want to show that they are in the same left coset, so that means what is this? This is A, the corresponding left coset of A, and this is the corresponding left cosets of A1. So if I want to show that these two left cosets are equal, then what I have to show?
AB inverse belongs to
Yes,
H.
A1 inverse A belongs to A intersection B, isn't it? I want to show this one, right? But what is the assumption? The assumption is AB equal to A1 B1. So from here, what I can do? I can multiply by this A1 inverse A and then this side by B1 inverse B inverse. So I get this, right? But this element belongs where? These elements
A
belongs to
intersection B.
A, this element belongs to B, they are equal. That means this element belongs to the intersection. Therefore, A1 inverse A belongs to A intersection B. That's what I wanted to prove. Therefore, this map is well defined because they define the same left coset in the quotient group. Okay. Now I need to show that this phi is a group homomorphism. Okay. So in order to show that phi is a group homomorphism, what I have to show? So the next thing wants to show that phi is a group homomorphism. So if you want to show that phi is a group homomorphism, then you have to just see that first operate two elements, apply phi is same thing as operating phi first and do the group operation. So let us check that. So phi of what is your AB? So one element say AB and the other element say A1, B1. So I want to show that phi of this element is same as phi of, so I want to show this is same as phi of AB into phi of A1, B1. Now let us see what is this. Phi of AB into phi of A1, B1. This is nothing but phi of AB, A1, B1, right? Now I would like to show that this is same as this one. But what is this side? Let us see. This side is phi of AB is nothing but A, the corresponding left coset of A, into this is the corresponding left coset of A1. You know now how to take the multiplication of two left coset. You just multiply the elements corresponding to that. So this is A1 corresponding left coset. So now if I try to make it equal to this one, then what I have to do? I have to bring this A1 somehow before this B, isn't it? But how can I do that? How can I bring this A1 before B? How can I do that?
By using a contained in normalizer definition.
Yes, yes, right. So I'm considering now this A1, A1 inverse B, A1, B1. So this term, if you see, this is nothing but this identity A1, A1 inverse. I have just written identity in this way. But now, what is this element? A1 inverse B, A1. This will be some element of
B.
B.
Yes.
So if I club this together, then this will be some element of, sorry, not from here. Yeah. So this will give me A, A1, and then some B2, B1, where B2 is A1 inverse B, A1. Okay. So now this is nothing but the corresponding left cosets of AA1 in this. Therefore, this phi is a group homomorphism. Is it clear to everybody? If it is not clear, please let me know. Fine. The next thing what I need to show that phi is a surjective group homomorphism. Is the map phi surjective? How I have defined? Phi of AB is nothing but the corresponding left coset. Is the map surjective?
Yes, and for every A, we will have an element AB.
Yeah, I can just take my B to be identity element. No.
Yes, ma'am.
So phi is surjective. Because I can have that phi of A is basically A intersection B. Okay. So this map is surjective. Now I would like to find out what is the kernel. So if I am able to show that the kernel is B, then we are done. So what was we wanted to prove? See, I wanted to show that AB quotient B is isomorphic to this. So for that I have defined this map phi from AB to here. Now if I am able to show, I have shown that this is a group homomorphism, this is surjective. Now if I am able to show that the kernel of this map is B, then by first isomorphism theorem I will be done. So now let us try to figure out what is the kernel. So what is the kernel? Kernel of phi. Kernel of phi means it is the collection of all the elements in AB such that phi of AB is identity. What is the identity element in the quotient group?
Intersection B.
A intersection B. Right? So now that means this is the collection of all AB such that A intersection B is the left coset AB. What does that mean? If this condition holds, then what does it say about A?
A belongs to
A
A
belongs
intersection.
to A intersection B.
A belongs to A intersection B. So kernel of phi is nothing but the collection of the elements AB such that A belongs to A intersection B. Okay, but what I want to show, I want to show that kernel of phi is equal to B. Correct? So now can you show that these two are equal? So I will just show as a containment that this is contained in this and this is contained in this. So note first that B is sitting inside this kernel, the collection of all AB such that A belongs to A intersection B. Is it true that B is sitting inside this one?
Yes, ma'am. Take A is equals to identity.
Yes, because this identity is in A, so that's why this is true. Okay. And on the other hand, what about the other inclusion? Since A intersection B is sitting inside B, so we have the reverse inclusion, isn't it? Is it okay? Is it clear?
Yes, ma'am.
Yes, ma'am.
Therefore, B is equal to kernel of phi. Hence, by first isomorphism theorem, I am able to prove that AB quotient B is isomorphic with A quotient A intersection B. So now somebody was saying why B is a normal subgroup of AB. Can you see why B is a normal subgroup of AB?
Yes, ma'am.
Because it is the kernel of a group homomorphism and the kernels are always normal subgroups. Therefore, this is a normal subgroup. So this is what the statement of the second isomorphism theorem. So most of the time we use the first isomorphism theorem almost all the places. Second isomorphism theorem is not used that much, but in sometimes in this Silos theorem and all we use second isomorphism theorem as well. Okay. Now I will do the third isomorphism theorem. So the proof of second isomorphism theorem is clear to everybody? At least give some
Yes, ma'am.
response. Okay, so now the third isomorphism theorem. So what does the statement say? So let G be a group and let H and K be normal subgroup with that H is sitting inside K. Then it says that K quotient H is a normal subgroup of G quotient H, and this G quotient H, quotient K quotient H is isomorphic with G quotient K. Okay, so what does the statement say? So let me just first tell the statement. So I have this group G, and then I have two subgroups such that K is a subgroup of G and H is also a subgroup such that H is sitting inside K. So I have this tower of subgroups. Okay. Then it says that this K quotient H, that means this subgroup, K quotient H is a normal subgroup of G quotient H. Okay. So basically your G quotient H, you are considering the quotient group, and you are trying to see how the subgroups of this quotient group look like. And in that case, you are saying that K quotient H is in fact a subgroup of G quotient H. And not only that, K quotient H is in fact a normal subgroup of G quotient H. And you are saying something more. You are saying that this isomorphism is true. So in some sense, you can think of like, okay, this cancel this H and this is G quotient K. Okay, fine. So let us first prove that K quotient H is a normal subgroup of G quotient H. First, we will prove this thing. First, we will show that K quotient H is a normal subgroup of G quotient H. So now our group is G quotient H, and I will show that in this group K quotient H is a normal subgroup. Okay, so for that, what I have to do, if I want to show that this is a normal subgroup of G quotient H, then what I have to do, I have to take elements from G quotient H, and then I have to see that if I take conjugation with of K quotient H, then I will again land into K quotient H, right? So any element of G quotient H, how does it look like? It will be a left coset,
GH.
isn't it? GH, right? So GH is an element of G quotient H. Okay, so let this belongs to G quotient H, and we want to show that GH, okay, take any element from K quotient H that will be of the form KH, right? And then GH inverse. I want to show that this belongs to where? K quotient
K
H,
quotient.
isn't it?
Yes, ma'am.
This is what I want to show, where KH is an element of this group K quotient H. First, tell me whether this is clear, that what we have to show. Only thing we are doing here is that instead of the group, I am considering the quotient group. Everything is same. Okay. Now my group I am doing is the quotient group, and on the quotient group the elements are nothing but left cosets. Look it carefully and tell me is this is fine. Is this fine?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, so now what is this multiplication? What is this? Let us see. Okay, so this is what? This is multiplication of left cosets, isn't it? So one is GH, then I have KH, and then I have GH inverse. What is GH inverse? What will be the inverse of this left coset GH?
G inverse H.
G inverse.
G inverse H. That we have already learned. Now, how do you multiply the left coset?
Multiplication of first element.
Element of
Right? Yes. So now I am having that this is this. Now, what about GKG inverse?
It belongs to K. As K.
GKG inverse belongs to K because
K is normal.
K
K is
is a normal sub. Correct? So therefore, this belongs to the left coset of H in K. Correct? So therefore, this is a normal subgroup. Therefore, K quotient H is a normal subgroup of G quotient H. Okay. Now I would like to prove the isomorphism. So in order to prove the isomorphism, again I will use first isomorphism theorem. So I would like to define a map from G quotient H, say phi, to G quotient K. Okay, I would like to define a group homomorphism between these two quotient group, and I would like to find out that the kernel will be the expected one. Then by first isomorphism we will be done. Okay, first of all, how to define this map?
phi of A is equal to phi of AK
Phi of
for all
GH is equal to,
phi of GK for
what is
all
phi?
G belongs to means GK simple GK
GK.
quotient.
Yes, yes, yes. So I am considered this is a left coset of H, okay, and I am sending it to a left coset of K, where G is varying over all the elements of G, right? Is this map fine?
Yes, ma'am.
So now I am not checking, check that phi is a group homomorphism. Okay. Next, we will first show that this is well defined. Phi is well defined. What to do in that case? That means I will start with two representation of the same left coset, and I will show that under this map phi they are mapping to the same element. Correct? So now what does it mean? That these two left cosets are equal means what? G2 inverse G1 belongs to H, isn't it? What does this mean?
G2 inverse G1 belongs to H.
Yes, G2 inverse G1 belongs to H. But what I want to show, phi of G1H is equal to phi of G2H. But what is phi of G1H?
G1K.
G1K I want to show is equal to G2K. That means what I want to show?
G2 inverse G1 belongs to K.
This belongs to K. But now I have G2 inverse G1 belongs to H. From here, can I conclude?
Yes, ma'am.
Yes, ma'am. S
Because
is group of K.
H is a
yes,
subset of K.
yes, because H is sitting inside K. So therefore, phi is well defined. Otherwise, I wouldn't have said this one. Okay. So this is also important
Ma'am,
that H is sitting inside
hello,
K.
ma'am.
Yes, 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 yes.
If we say that let G1 and G2 be two elements belongs to G, with G1 equal to G2, then GH1 equal to GH2. The G1 G1H equal to G2H,
Hmm.
uh, the- and G1K equal to G2K. Then f of means phi of G1H equal to phi of G2H.
Yes,
Then also phi is well defined.
yes, yes, yes. That's what we have done here, no? Means you are saying in this direction, right? You are saying that this is true, therefore this is true, therefore this is true, therefore this is true, therefore this is true,
No. Yes, ma'am.
right?
Yes, ma'am.
Yeah, so that is what we have done. I only thing just I have gone from both the direction so that it will be easier for you to understand what is the what we are trying to do. Okay.
Yes,
Now we need to check in order to apply first isomorphism theorem. There
अरे
is another.
गाड़ी वाला से आपका बीड़ी ठगी गोल काय
Please
बीड़ी ठगी गोल
mute
काय जाए.
yourself. So now I need to check that this map phi is surjective. Is the map phi surjective? Is the map phi
Yes,
surjective?
yes, ma'am.
Yes, ma'am.
Yeah, because you
For
just consider
G
whatever
belongs
this
to G.
G, yeah, you can consider the corresponding left coset in G quotient H. So this map is surjective. Okay. So phi is surjective. Next, I need to find out the kernel of phi. What is the kernel of phi? So kernel of phi is the set of all left cosets such that phi of this is equal to identity. What is the identity in G quotient K?
H,
K.
H.
K, right? So this is nothing but all GH, the left cosets such that what is phi of GH?
K.
It is nothing but GK. GK is equal to K. What does that mean that GK is same as K?
G belongs to K.
Such that G belongs to K. That means this is nothing but the left cosets of KH. Right? So I'm considering all the left cosets GH where G is varying over K. That is nothing but the left cosets of K quotient H, this quotient group, right? Therefore, my first isomorphism theorem what is true? That G quotient H, quotient the kernel, which is K quotient H, is isomorphic with G quotient K. Is this proof clear?
Yes, ma'am.
Okay, good. So these are the three isomorphism theorem. Now I would like to give you the relationship between the subgroups under a group homomorphism. So let me write it down. So let F from G to G tilde be a surjective group homomorphism and K be the kernel of the group homomorphism F. Then it says that then there is a bijective correspondence between these two sets. What are the two sets? One side I am considering that subgroups of G containing K, and another side I am having subgroups of G tilde. Okay. So it is saying that the subgroups of G containing this kernel K are in 1-1 correspondence with the subgroups of G tilde. That means for every subgroup in G containing the kernel, I will be able to associate one subgroup of G tilde, and for every subgroup in G tilde, I will be able to associate one subgroup of G which contains the kernel. Okay, so this gives you the description or the association between the subgroups between two groups under a group homomorphism. But how do you associate these subgroups? That is the question. How do you associate this subgroup? So suppose I start with a subgroup H in this side. I should associate a subgroup in this side. So what will be the natural correspondence? Where should I send this H?
Image of H under phi under F.
Under F. So I will send under F this subgroup. So F of this, that will be a subgroup of G tilde. And what will be the reverse? That means I start with suppose a subgroup here in G tilde. Where should I send it to?
Their inverse image.
Yes. That means
Inverse.
F inverse of H tilde. Okay. So this correspondence is given by these maps, and if I moreover restrict this bijection over normal subgroups, to the normal subgroups, then also I will get a bijection. So normal subgroups of G containing the kernel K is in 1-1 correspondence with the normal subgroups of G tilde. Is this fine? That means if I start with a normal subgroup here and go via this map, then I will land into a normal subgroup of G tilde, and vice versa. If I start with a normal subgroup of G tilde, then via this map I will get a normal subgroup of G containing the kernel. That's what it says. Okay, so now I will just quickly draw the outline. You fill up the gaps of the proof. So I will do it very quickly. So what you need to show, that I start with a say H is a subgroup of G containing K. Okay. Then of course if I apply F, then F of H is a subgroup of G tilde. Okay. Now what you want to show? You want to show is the following. So first you can check that this will be a subgroup, so that so check this thing, that this will be a subgroup, and then further you try to show that you started with H and then you applied F, you get a subgroup in G tilde, and then you apply F inverse on this, you should get back your H. Okay, that is what you want to show, first thing. So how do you show that? You just show both the containments, then it will be done. Okay. And on the other hand, what the next also you want to show, you start with any H tilde and then apply F inverse on this one, and then if you apply F again on that, you should get back your H tilde. Okay. So this is the another thing you would like to show. So again you will show by this containment only. Try to show these two facts, and then on the normality is not difficult. Okay, so I give both as an exercise. This is a routine checkup that you need to do. Try to do by yourself. You are not able to do, in that case you tell me, I will solve it. Okay, but first try. This is a routine checkup of how to do this thing. So it somehow says that how the subgroups of these two groups are related via this group homomorphism. Okay, fine. Is it clear?
Yes, ma'am.
Okay, so then I will stop here today. So next week I will start with the group action. So please, whatever I have covered so far, this group action is little bit much more deeper concept. So you study well whatever I have done so far, all the things we will be using while we will be doing this group action thing. Okay. And I will upload one more exercise tutorial sheet today, and that we will discuss in next week Friday's class. Fine.
Yes, ma'am.
Yes, ma'am.
Okay then. Any other